Chaos marks the end of classical science, but as we'll see, it does not overthrow determinism and the use of mathematics. The touchstone for chaos is something called the logistic growth equation. This mathematical expression is trivially simple. For a century it was thought to be completely understood. But the logistic equation is like an orchid seed, an apparently simple thing which, when treated in the right way, will grow into a fantastic and beautiful flower. The logistic equation can generate an astounding variety of patterns, some of them infinitely complex. This is done through iterations of the equation, meaning that the calculation is reapplied to every result to produce a sequence of numbers. Although the logistic equation uses only multiplication and subtraction, in many cases it's impossible to predict the sequence of numbers that it will produce. Lurking in the heart of this simple mathematical expression are infinite complexity, apparent randomness, and unpredictability that, taken together, are known as deterministic chaos. What is the equation? Simply this: r times x times 1 minus x equals the next value of x. In other words, the growth rate r multiplied by the current value x multiplied again by 1 minus the current value of x equals the next value of x. Today, this equation is acquiring a status that's equivalent to Einstein's E equals mc squared as an equation that symbolizes a new way of seeing the world. The logistic growth equation was first proposed in the 1840s by the Belgian mathematician Pierre-François Verhulst. He believed that it captures the basic features of growth in almost any biological population. He started with the idea that every species has its own intrinsic growth rate, the r in the equation. This intrinsic rate would be achieved only under ideal conditions. For example, a population of a particular species may double every year. Here, r equals 2. This continual doubling is called exponential growth, and it produces a sequence like 2, 4, 8, 16, 32, and so on. This is the sort of growth that the English economist Thomas Robert Malthus was concerned about when he said in 1798 that exponential growth of the human population will outstrip incremental gains in food production. Malthus believed this would produce permanent poverty. But Verhulst saw that growth conditions are never ideal. No population will ever grow as fast as if conditions were perfect. Real populations must have shelter and food in order to survive and reproduce. When a habitat becomes overcrowded, resources may be strained. This means the growth rate declines. In cases of extreme overcrowding, the growth rate may even become negative, producing a loss of population. To account for the ever-present limitation of resources, Verhulst added a mathematical term that represents the effects of crowding. That's why he called his equation logistic, based on the French word logis, meaning a dwelling place. The logistic growth equation accounts for limitations in the habitat. But the importance of this equation is not limited to biology. In one form or another, it is now used in a wide variety of disciplines. The logistic growth equation is the most basic mathematical expression of the conflict between two universal principles: the drive to growth and the limits to growth. As the biologist Robert May writes,
although I shall henceforth adopt the habit of referring to the variable x as the population, there are countless situations outside population biology where the basic equation applies. There are other examples in biology, as in genetics or in epidemiology. Examples in economics include models for the relationship between commodity quantity and price, for the theory of business cycles, and for the temporal sequences generated by various other economic quantities.
Verhulst and those who followed him thought they were working with a normal, well-behaved equation. It was Robert May who in the early 1970s discovered the chaotic behavior hidden in the logistic equation. Originally trained as a physicist in Australia, May later moved to the United States and then to England. Along the way, he became interested in applied mathematics and population biology. He also began to investigate nonlinear equations like the logistic growth equation. In 1973, May published his first results showing that simple equations produce chaotic results.
The very simplest nonlinear difference equations can possess an extraordinarily rich spectrum of dynamic behavior, from stable points through cascades of stable cycles to a regime in which the behavior, although fully deterministic, is in many respects chaotic or indistinguishable from the sample function of a random process.
But how can a simple mathematical expression yield such bizarre behavior? To understand this, we need to examine two concepts that have fundamentally influenced many surprising developments in mathematics and science. These are the attractor and the bifurcation. First, let's do a thought experiment to explain what an attractor is. Imagine dropping a marble into a large rounded bowl. It will roll around a bit, but eventually it will come to rest at the very bottom. The lowest point in the bowl is the attractor, and the bowl itself is called the basin of attraction. The marble rolls around before finally coming to rest, and the path it takes is the system trajectory. Most dynamic equations essentially describe a situation similar to a marble in a bowl. But the bowl may not be simple. It may be like a double sink containing two basins, or it may contain many basins. We can't say where the marble will come to rest until we know into which basin we dropped the marble. Another possibility is that the bottom of the bowl has a small hump in it. In this case, the lowest part of the bowl forms a ring around the hump. The attractor is then a circle, and the marble will end up rolling around in this channel. Attractors represent stability in a system. No matter what the starting position, the system will move to an attractor and remain there. If the system is pushed away from the attractor by an outside force, the system eventually will return to that attractor, just as the marble rolls back to the bottom of the bowl. But when a system evolves, its attractor may change. For example, a smooth-bottomed bowl may begin to bulge upward to form a small hump, or a single attractor may split into two. This type of change, where an attractor becomes more elaborate or splits, is called a bifurcation. Bifurcations increase the possibilities available to a system, and they're very interesting to mathematicians and scientists. For the logistic equation, the shape of the attractor and the kinds of bifurcations possible all depend on the population's intrinsic growth rate. For moderate growth rates, there is only a single attractor and a single stable population level. The population grows or shrinks until that level is attained, as illustrated in this musical pattern. But for higher growth rates, the population does not stabilize. A high growth rate in species that have overlapping birth cycles causes the population to overshoot the sustainable level and then to crash. If the birth cycles don't overlap, for example as with some insects, the population will bounce back and forth between high and low levels in what is called a two-point cycle. Here, the original attractor has bifurcated. As the growth rate, that is, the factor r in the equation, is increased to higher and higher levels, the attractor will undergo further bifurcations, so the population will enter four-point cycles.